Hi, here we have AP Calculus BC problem, that is we have to evaluate the given limit. Okay, so to evaluate the given limit, what I'm going to do is I'm going to substitute the given limit for x directly into the function. That is, I'm going to plug in x is equal to 0 into the given function, then I'll be getting cotangent 0 to the power sine 0. Okay, so I know that cotangent is a reciprocal of tangent. So we can write cotangent 0 as 1 over tangent 0. So using trigonometric ratio table or unit circle, we can get the value of tangent 0. So the value of tangent 0 is 0. So a non-zero number 1 divided by 0 will result infinity or undefined. So finally the value of cotangent 0 is infinity to the power. So we know that the value of sine 0 is 0. So when I directly substitute the given limit for x into the function, I'm getting infinity to the power of 0, which is indeterminate form. Whenever I get indeterminate form as a result in evaluating a limit, so what we'll be trying to use is we'll be trying to use L'Hopital's rule to evaluate the given limit. But if I want to use L'Hopital's rule for the given limit, the function in the given limit must be in the form of f of x over g of x. That is in the form of a fraction. So where we have the variable x in both numerator and denominator, so that it will be easier for us to use L'Hopital's rule in the given limit. And the given limit, the function we have over here is not in the form of a fraction. That means it's not in the form of f of x over g of x. And moreover, the given function contains variable x at the exponent. Okay, so whenever we have this kind of function in evaluating limits, we have to use logarithm to evaluate this kind of limits. So we use logarithm when you have variable at the exponent. Okay, to use logarithm to evaluate this kind of limit, what I need to do is first I have to assign new variable for the given function. So here, what I'm going to do is I'm going to assign a new variable y for the given function. That is, I assume y equals to cotangent x to the power sine x. Okay, the next step what I need to do is minus to get rid of the variable at the exponent. So that is why we use, I'm saying that we have to use logarithm. Until we have variable at the exponent, it will be difficult to evaluate this limit. So we have to get rid of this variable at the exponent. So for that, we have to use logarithm. If I use logarithm, I can use the properties, particularly the power rule of logarithm, and I can bring this exponent in front of the logarithm. Okay, now what I'm going to do is I'm going to take natural logarithm on both sides. Then I'll be getting ln y equals to ln of cotangent x to the power of sine x. Okay, here the next step, if I use the power rule of logarithm, I can move this exponent in front of the logarithm. Then it will become sine x times ln of cotangent x. Okay, so the next step, what we can do is like we can write this sine x as 1 over cosecant x. So using reciprocal trigonometric identities, we can write sine x as 1 over cosecant x because the reciprocal of sine is cosecant. So why should I write this sine as 1 over cosecant? As I told you earlier, we should be trying to get the form f of x over g of x. So that even if I get the indeterminate form again, so I can use L'Hopital rule. If I want to use L'Hopital rule, then the function has to be in this form, f of x over g of x. So that's the reason I'm writing sine x as 1 over cosecant x. If I write sine x as 1 over cosecant x, I'll be getting the form f of x over g of x on the right side. Just a moment, let me clear this. Okay, so what I'm going to do is I'm going to write ln y equals to, instead of sine x on the right side, we can write 1 over cosecant x times ln of cotangent x. So in the next step, ln y is equal to, we can multiply this 1 and natural logarithm, then we'll be getting natural logarithm of cotangent x over cosecant x. Okay, here, so now I got the form, I got the right side, the stuff on the right side, I got it in the form f of x over g of x. So here we have variable in both numerator and denominator. So now I can take the given limit on both sides. So then I'll be getting limit x tends to 0, ln y equals to limit x tends to 0, ln of cotangent x over cosecant x. Okay, here when I apply the given limit, even if I get indeterminate form as a result for this limit, I can use L'Hopital rule in this step, because here the function in this step is in the form of f of x over g of x. Okay, anyways, let's plug in the given limit for x, that is 0. So then I get ln of cotangent 0 over cosecant 0. Okay, so to evaluate cotangent 0, what we can do is we can use tangent, because cosecant is a reciprocal of tangent. So cotangent 0 can be written as 1 over tangent 0. We know that the value of tangent 0 is 0, 1 over 0 is undefined. Okay, already we have done this. So for cotangent 0, we can plug in infinity or undefined. So ln of undefined over. So cosecant 0. Cosecant, already we know that cosecant is the reciprocal of sine. So we can write cosecant 0 as 1 over sine 0, and 1 over the value of sine 0 is 0, 1 over 0 is undefined. So the value of cosecant 0 is undefined or infinity. So natural logarithm of infinity is still infinity. So infinity over infinity, still again I am getting indeterminate form. So since we get indeterminate form, we can use L'Hopital's rule. So here we have a doubt where we have to use L'Hopital's rule. You just consider the step where we have applied the limit. So this is a step we have applied the limit. So to use L'Hopital's rule, consider the previous step. This is a previous step we have. So in this step only we have to apply the L'Hopital's rule. So whenever I get indeterminate form, I use L'Hopital's rule in limit. But to select the step in which we have to use L'Hopital's rule, so we have to consider the step which comes right before where we have applied the limit. So this is the step we have applied the limit. You just consider the step which comes right before it. That's over here. So now I can take this step as it is to the next page, and I'm going to use L'Hopital's rule. Okay, now let me take this step. Limit x tends to 0, ln y equals to limit x tends to 0, ln of cotangent x over cosecant x. So I'm taking this step exactly on the next page. Now I'm going to use L'Hopital's rule. Okay, so now when I use L'Hopital's rule, I have to keep the stuff on the left side as it is. That is, I'm writing this one, limit x tends to 0, ln y as it is. So I have to use, I have to apply L'Hopital's rule only to the stuff on the right side. So using L'Hopital's rule means we have to find the derivative of this numerator and denominator separately. Actually, in this function, we have variable both in both numerator and denominator. Whenever we find derivative of this kind of functions, we'll be using coefficient rule, because we have variable in both numerator and denominator. But when I use L'Hopital's rule, I'm not supposed to use a coefficient rule. I have to find the derivative of the numerator and denominator separately. Okay, let me write the given limit as it is, limit x tends to 0. When I find derivative of this natural logarithm of cotangent x, it will be 1 over cotangent x. And by chain rule, when you do further derivative of this cotangent x, it will be negative cosecant square x over. So the derivative of this cosecant x is negative cosecant x times cotangent x. Okay, before we apply the limit, we have to simplify this one over here. Okay, whenever I want to simplify a function which contains the trigonometric ratios like cotangents, cosecant, something like that, what we'll do is we'll be trying to write the given function in terms of sine and cosine. Okay, let's do that. Limit x tends to 0. This 1 over cotangents can be written as tangent x, and this negative cosecant square x can be written as negative 1 over sine square x over negative, this cosecant x can be written as 1 over sine x, and this cotangent x can be written as cosine x over sine x. Okay, so the next step, limit x tends to 0. Further, this tangent x can be written as sine x over cosine x times negative 1 over sine square x divided by, and when I multiply negative 1 times cosine x will be negative cosine x over sine x times sine x will be sine square x. So the next step, it will be limit x tends to 0. Sine x times 1, negative 1 will be negative sine x over cosine x times sine square x. over negative cosine x over sine square x. Okay, here limit extends to 0. Okay, I'm writing this fraction as it is, that is negative sine x over cosine x times sine square x. And I'm changing this division as multiplication, and I'm taking reciprocal for this one. It will be negative sine square x over cosine x. So here I can cancel the sine square x and sine square x. So I'm getting, so here we have 1, here we have 1. So negative sine x times 1, here we have negative 1. So negative times negative will become positive, sine x times 1 will be sine x. And cosine x times cosine x will be cosine square x. Okay, let me continue on the next page. And let's take the stuff we have on the left side as it is. That is limit x tends to 0, ln y equals to, we have negative times negative will become positive, sine x times 1 will be sine x. In denominator, we have cosine x times cosine x will be cosine square x. And we have limit x tends, okay, so that's all the simplification we can do. Now I can plug in the limit of x into the function, then I'll be getting sine 0 over cosine square 0. So we know that the value of sine 0 is 0 and cosine 0 is 1, but we have square for cosine, so 1 square. So 0 over 1 square is just 1. Finally, we get limit x tends to 0, ln y equals to 0 over 1 is 0. Okay, now what we can do is on the left side, we can use composite function theorem. So composite function theorem means like whenever we have natural logarithm inside the limit, using composite function theorem, the natural logarithm can be moved out of the limit. So that's what said by the composite function theorem. That is, this natural logarithm that we have inside the limit can be moved out of the limit. Then I'll be getting natural logarithm of limit x tends to 0, y equals to 0. Okay, now already we know that what is y equals to. We have considered y for the given function, that is cotangent x to the power of sin x. So that is we have taken over here. So y equals to cotangent x to the power of sin x. So y can be replaced by cotangent x to the power of sin x. Okay, but before that, I think we can do one more step. That is, we can actually, we have this equation in logarithmic form. It can be converted to exponential form. That is, if I move this natural logarithm to the other side of the equation, so we just have to consider the base of this natural logarithm. We know that the base of the natural logarithm is e, and we have to take this 0 as the exponent of this e. So whenever I move natural logarithm from one side of the equation to the other side, we just have to consider only the base of the natural logarithm. Base of the natural logarithm is e, and the value which already exists on the other side will become exponent of this the base e. So we get limit x tends to 0, y equals to 1. Okay, let me continue. So we got limit x tends to 0, y equals to 1. Already we know what is y equals to. So because we have considered the given function, that is cotangent x to the power of sin x. We have assumed the variable y for cotangent x to the power of sin x. So now y can be replaced by cotangent x to the power of sin x equals to 1. So I have evaluated the given limit, that is limit x tends to 0, cotangent x to the power of sin x, that is equal to 1.